All right, so chapter 5 is about the normal distribution mostly, but we're going to start by talking about standardizing. So we're going to do some of this vocabulary and we may come back to it. So standardizing is expressing, oh my goodness, I can't write, expressing the distance from the mean in standard deviations. So we'd measure how many standard deviations something is away from the mean. So if your standard deviation is 2 and your mean is 4, then 0 would be 2 standard deviations away because your standard deviation is 2. So that's what standardizing means. A standardized value is called a z-score. And the formula for this is not, I don't think, unless they changed it. I'll have to find the updated one to put on Canvas. But the formula I don't think is on your formula sheet that you can use. So I don't know, but it is, X is the value that you're trying to standardize, minus the mean divided by the standard deviation. Remember, this is mean and standard deviation. Or if these are for population, this would be for a sample. All right, same thing, mean, standard deviation. X is the value you're trying to standardize. So this gives you that distance from the mean and standard deviations because you're subtracting the mean from your data point, which gives you the distance away, and then you divide it by the standard deviation. So that's going to give you how many standard deviations you are away from the mean. And I just defined z-score, but I'll just reiterate what we wrote up here. So it tells how many standard deviations away from the mean a data point is, and it standardizes it. Now, why do we want to standardize stuff? So that we can compare them. We'll come back to these other ones. I don't remember what this was. I think we might do this in class. We will do it in class. Let's put it that way. We will do this in class at the beginning of class. So anyway, standardizing variables, height of women, height of men. There is not a mean and standard deviation on here. This is what I found from Googling. Don't get mad at me if you think I'm wrong. So the mean for women's heights is supposed to be 65 inches, so 5 feet 5. The standard deviation is 3.5 inches. And for men, the mean is supposed to be 69.1 inches, so 5 feet 9. And the standard deviation is 2.9 inches. All right, so that's mean and standard deviation of men and women. So why would you want to standardize that? Because women are typically smaller than men, so it's hard to compare it. Like my brother is 6 feet 5 inches, and I'm 5 foot 7. Like it's hard to compare. I want to compare myself to other women and him to other men to see, you know, is he really taller than average? That sort of thing. So I'm 67 inches tall. My brother is 72 inches tall. Who's taller comparatively? So this is going to be me. Here's my z-score. So my z-score is going to tell me. So let's see, 67 minus the mean divided by the standard deviation. So that's 2 over 3.5, which is, you usually want to do 2 decimal places on a z-score. So 0.57. A z-score for my brother, he's 72. My brother's actually taller than that, but that's okay. It's minus 69.1 over 2.9. And if I work that out, that one is 1. All right, so comparatively, he is taller. When you compare him to the rest of the male population, he is taller than I am compared to the rest of the female population. So he is. Okay, so then another one, SAT versus ACT. So you get a 30 on the ACT, you get a 700 on the SAT. I don't know. How do you know which one's better? All right, this is where doing a z-score and standardizing things is actually kind of important. So you took the SAT and scored 550. Your friend took the ACT, scored 30. Which score is better? And they give you the standard deviation. So we'll do the SAT first. 550, your data point minus the mean, divided by the standard deviation. That is 0.5. And the ACT, you have 30 minus the mean, divided by the standard deviation. That is 2. So obviously the ACT is the better one. Your friend did better relative to everyone else who took the ACT versus you relative to everyone else who took the SAT. So it just standardized it. They're two completely different grading scales, but that way you can see kind of which one did better relative to kind of the norm. All right, we're going to go back up and do a little bit more vocabulary. So a normal model is a family of models that are unimodal and symmetric. So unimodal has one peak. Symmetric means that it's a mirror image on either side. The middle, the very middle, the peak, is the mean and median. All right, because for symmetric one, they are the same. And the standard deviation determines the kind of the flatness of the curve, so to speak. Like if it's really steep, I'm not drawing this very well, or just kind of a little curve. All right, but a normal model is a bell curve. So it determines, I'm going to say steepness. We already know parameter and statistic. The standard normal model, the mean is 0, and the standard deviation is 1. All right, and we denote this by saying n for normal model, and then you put the mean and standard deviation in here. All right, mean and standard deviation. We're going to do an example with this. This is a rule for how much of your data is within so many standard deviations of the mean. And then normal percentile, I'll just throw in here, and we're not going to talk about the other ones. A percent of data found at that z-score or below. So we talked about percentiles just a little bit with ogives. That means if it's the 20th percentile at that z-score, 20% of the data is below it, basically. Okay, so let's look at this example and then the other ones are going to be for the next day. All right, so some IQ tests are standardized to a normal model with a mean of 100 and a standard deviation of 16. Draw the model for these IQ scores. So what we're going to do is we're going to have a little axis here, and we're going to draw, or I'm going to attempt to draw, a bell curve. Oh, look how nice. Right smack dab in the middle, with my bad vertical lines again, I'm really trying, the mean. All right, so our mean is 100. And we're going to do little divisions on either side. We're going to do 3 divisions on either side. And we're going to go a standard deviation away from the mean for each division. Okay, so I'll show you what I mean here after I draw these. This takes a lot of concentration. Okay, so on this side, we are going to add a standard deviation each time. So our standard deviation is 16. So 100 plus 16 is going to be 116. Then we're going to add another standard deviation. So 116 plus 16 is 132. And then we're going to add another standard deviation. 132 plus 16 is 148. And then we're going to do the same thing on the other side, but we're going to subtract it. All right, so 100 and then back subtracting. So I'm going to cheat. So this is 84. And then subtract another 16 is 68. And subtract another 16 is 52. All right, what the 68, 95, 99.7% rule says is that 68% of your data is within one standard deviation of the mean. So 68% of people's IQs are between 84 and 116. That seems low, I feel like. I don't know. I have no idea. I don't know what my IQ is. So this is 68% is between those two. All right, so that's what the 68% rule says. 95% of your data is within 2 standard deviations. All right, so 95% of people's IQs are between 68 and 132. And then 99.7 is within 3 standard deviations. Okay, so 99.7% of people's IQs are between 52 and 148. So 68% within 1 standard deviation. 1 standard deviation on each side. 95% is 2 standard deviations, and 99.7% is 3. All right, now you can actually break this down further, because remember, the mean cuts it in half. So if this is 68%, each half is 34%. Okay, and then you can do that all the way down. You may have to do that for one of these. So B, in what interval would you expect the central 95% to be found? Well, we just labeled it 68 to 132. About what percent of people should have IQ scores above 116? So that's going to be this little space, right? The whole thing should add up to 100%. Okay, to the left of 100 is 50% of the data, because 100 cuts it in half. All right, so we want above 116. We're actually going to find what's below 116 and then subtract from 100. So 50% is below 100. All right, then we're going to add to that this little space. And I said 100 cuts it in half. So if this is 68%, if this line is 68%, then half of that's 34. So that is 84. But that's the wrong way. That's below 116. So we want to do 100 minus 84 to get our answer, which is 16%. All right. So that was a complicated one. D, about what percent of people should have IQ scores between 68 and 84%? All right, so we have to figure out some way of finding that, because we don't have that labeled. We know this is 68%. We know this is 95%. We could do 95 minus 68, which is 27. Yes. That is what these little spaces are. All right, both of these spaces between 116 to 132 and 68 to 84, both of them together are 27. So we need to divide that in half, because they should be exactly the same. They should be mirror images. So we can just divide it in half, and that is 13.5%. All right, and then the last one, about what percent of people should have IQ scores above 132? So we can do something similar. All right, between 68 and 132 is 95%. That leaves 5% for both ends. All right, the 132 and above is half of that. So we're going to do 100 minus 95, that's 5%. And then we're going to divide it in half, and that's 2.5%. All right, so you can figure out some of these percentages without having to break this down any further. So that's the 68, 95, 99.7 rule.